Then I would like to introduce the speaker today. Welcome to the Physics Colloquium. The speaker today is Professor Gino Isidori. He's actually originally from Italy. He did a PhD at University of Rome, La Sapienza. And after that, he moved from SLAC to the National Lab in Italy. He was a fellow at CERN in Geneva, a famous European lab, and became a professor at the Scuola Normale Superiore in Pisa. And he had many appointments at CERN and also at the Technical University of Munich. And since 2014, he's a full professor at University of Zurich, where he has a pretty amazing group working particle physics and cosmology. He is a very well a person in the field of physics beyond the standard model in particle physics. In the last years, he has been very active. He wants to understand new experimental results coming from CERN and has to do with flavor physics. And this is what he will talk about today. Then please, Gino.
Thanks a lot, Paul. Very nice to kind of this introduction. And okay, so let me start to share. Okay, you see the screen?
Yes, but it's not full screen yet.
Yeah. Sorry, you full screen. Okay, full screen.
Yes.
Let me try to. Sorry to minimize these things of the. Okay, so now I don't see you, but okay, I hope you see me.
Yeah, it's good.
Okay, now perfect. Now I even have a small window where I see you. Okay, so it's really pleasure to be here. Pleasure to give this seminar. Not to be there, but it's a pity not to be there. But it's a pleasure to give the seminar. And as Pavel told you, what I will discuss today is I'll try to give you an overview of recent development in flavor physics, discussing the old problem that we had with flavor since a long time, and then the new development that are related to these interesting results in B-meson decays, this lepton flavor universality violation, and which is what we can call the new puzzle. And I will tell you some idea that we have how to solve this new puzzle and to connect it to the old one. So let me start from, I will start at the general, and then I will go more into some technical and more recent development. So as you know, all the macroscopic phenomena we observe are well described in particle physics at the fundamental level by the standard model. This beautiful theory, actually we call it model for historical reason, but we should really call it a theory because it's a bit like general relativity, so it's really well consistent theory. And however, this theory has some deep unsolved problems, among which the two ones that I will touch today are the famous hierarchy problem and the flavor problem. That is, there are a lot of parameters in this theory that we cannot explain, okay? And we would like to explain they are a bit non-natural. And of course, there are other problems related to observation in the sky. I mean, the neutrino masses, dark matter, dark energy. So all these things let us to think that the standard model is, despite it's beautiful, self-consistent, and is well tested in experiment, but still we think that it's only an effective theory, or if you want, the limit of a deeper theory that contains extra layers. So, and this we know technically how it works. So when we consider the standard model as an effective theory, we think that, okay, there is a ultraviolet completion, so a theory that contains more degrees of freedom. And in these degrees of freedom, we think they are heavier, okay? Because indeed, what has been found at the Large Hadron Collider at CERN is that we found the Higgs boson, so the last missing piece of the standard model. So this basically has constrained the standard model spectrum. That it's, you see it here. Actually, the Higgs is not the heaviest particle. The heaviest is the top. But this defines the spectrum of the standard model. And then after that, there is certainly a mass gap because we don't see any other state close by in mass. So deduce from the experiment that there is a mass gap. And therefore, it's and what we would like to understand is, okay, how big is this mass gap and what complete the theory. So if you want, again, just to make an analogy, we identified, if you want, the long range structure of the model, the big pieces, and we would like to understand if we can break them to smaller pieces, more fundamental pieces. And we understand also how the long range interaction of these pieces, so the rule how they interact, and again, we want to understand if there is something more microscopic. And we know this is a very difficult problem, reconstructing a UV theory if you only know the low energy content. And we know that because in a sense, we passed already through this phase many years ago, actually, when we had the Fermi theory, which was an effective theory, and to reconstruct the standard model, it took essentially 35 years. So why this is difficult? Because when we go from the UV to the low energy theory, to the standard, to the effective theory, we basically integrate out some degrees of freedom. So we basically project some information, and therefore we lose information. So how to do this? It's easy, okay? We know it, I mean, technically complicated, but we know how to do it. Again, for example, to go from the standard model to the Fermi theory, it's easy. But now we want to do the inverse, so to go from the standard model to something above, where, let's say, a four-fermion interaction, for instance, is described by some new mediator. Of course, this is difficult because there are different high energy theory that can give rise to the same low energy theory. So how we can proceed? Of course, if we could see some new particle, would be easy, but we don't see them. We see that there is this mass gap. So what we can still do, I mean, is still to understand if there are some unnatural feature in what we observe in nature, okay, in this interaction of the long-range pieces. If there is something unnatural that, for instance, something that we cannot explain with the building blocks that we have, then it's an indication that there is something more to be discovered. And so which are the unnatural features of the standard model view as an effective theory? As I said, say we cannot put here dark matter, dark energy, because these are really things that which are not described in the theory. Okay? We cannot really describe with any of the parameters of the theory. On the other hand, there are two problems which are really seen as problem of the theory as an effective theory, which are the electroweak hierarchy problem, that is the instability of the Higgs mass under quantum correction. So we know that we have only one mass parameter in the theory, the Higgs mass, and this mass is unstable with respect to quantum correction. So we think there must be something not too far from the electroweak scale to stabilize the Higgs. This is a well-known problem. But then there is another problem, which is the flavor problem, which sometimes is ignored, and this is where I will focus my attention. And this problem, now I stated for the first time that we will discuss in more detail, is the fact that we have a kind of tuning of the coupling to describe fermion masses. So actually how the fermions are coupled to the Higgs, which is how we describe the mass, it contains a lot of free parameters that we are not natural because span several orders of magnitude. So these are two unnatural features of what we see in the standard models and effective theory. And what I will try to argue in the rest of this talk, that is worth trying to put these two problems together, at least try to solve them not separately, which actually has been the approach which has been pursued so far by many people, because of course it's easier to separate the problem and try to solve them separately, but okay, maybe in nature it's not done this way. So I will try to argue that actually it's important to try not to forget this one, which is the flavor problem. So let's give a closer look to the flavor problem. What is the flavor problem? Actually, this is a very old problem, which actually was there even before the standard model was completed. And probably the first who formulated the problem in a clear way was Isidori Rabi, who when the muon was discovered, when the first particle with the same quantum number of something that we already know, that is the muon, which is the same quantum number of the electron, has been discovered, people start to ask why we have that. We in a sense, we don't need it to describe matter. And that is the problem, why we have this duplication of triplication of families. So now let's go to the standard, try to be more quantitative. So in the standard model, if you look at the standard model Lagrangian, we have the gauge sector, so the gauge sector is a sector that sees the fermions, the different families, in a universal way. So for instance, here we don't distinguish electron and muons, okay, they are identical. Then we have the Higgs sector, which is the one that breaks this degeneracy of the different families because of the interaction of different families with the Higgs. And this is the way we describe the masses. So we describe the masses as the fact that the Higgs get a wave and therefore generate masses. And then, okay, if you think that this is an effective theory, this must be something else, so a tower of higher dimensional operator, which for the moment we have not seen. But let's concentrate here on the Higgs sector, and in particular on this Yukawa interaction. So this Yukawa interaction is the one that we put to describe fermion mass. And so we have this structure with three families, as you know. So the first family with down up quark, the electron, the second family with charm, strange muon, the third family with top, bottom, tau. And you see that the masses span several order of magnitude. So the Yukawa coupling here, so this coupling between fermions and the Higgs have a very hierarchical structure. So here I try to give a graphical representation of the up quark Yukawa coupling, which is the one for the up quark, where you see there is this big entry here, which is the top quark Yukawa coupling, which is 1. Okay, and then we have a tiny entry that you don't see here, which is the up quark, which is 4 order magnitude smaller. Okay, and then we have something a bit bigger, which is the mixing between the third generation and the second one, and so on. So it's clearly a very hierarchical structure, which doesn't seem to be natural. Now, okay, this is the flavor structure of the Standard Model. This peculiar structure here, which is sometimes called the Standard Model flavor problem, because we don't have an explanation why the structure is like this. Of course, we can put it by hand in the Standard Model at free coupling, but it's clearly a bit ugly. The other problem still related to flavor is the fact that, okay, if we think there is something else, okay, there should be other operators, okay, due to the fact that there are some UV degrees of freedom, and these UV degrees of freedom will couple to our light generation. So for instance, they will induce naturally coupling like here, psi bar I, psi bar j, so a coupling between two different fermions, okay, is a 4 fermion interaction, so something like this, like a Fermi theory, which would contribute, for instance, to K-bar mixing. And we don't see these things here, okay, beside a few anomalies, which I will comment on later. So we have a long list of bounds on coupling of this type, okay, which actually, if you think this coupling is 1 and is suppressed by a scale, because these are higher dimensional operator, these scale have to be very heavy to be compatible with data. Actually here, I show you a plot where you see that the bound on this scale derived by the experiment on possible higher dimensional interaction in the sector of flavor, which range 10 to the 5, even 10 to the 4 tera electron volt, so well above the Higgs mass, which on the other hand is the other reference scale of the theory. So we would like to have something close to the Higgs mass to stabilize it, but we don't see it. So this is the second problem of flavor. So we have, if you want, the new physics flavor problem, that if there is some new physics, this new physics should couple very little to the fermions, especially the light fermion of the Standard Model, because we have strong bounds. So these are the two problems. Now, these problems actually are known since a long time. So trying to summarize what we see in the Standard Model, we have the gauge sector, which is trivial. I mean, so the different families are seen exactly in the same way by the gauge forces. There is no distinction between first, second, third generation. And here everything is just dictated by the quantum number. So we don't have freedom to distinguish the families. On the other hand, here, we might have we can think that this peculiar structure of these Higgs coupling, which are very small for the first generation, very big for the third generation, and the fact that we don't see anything here is an indication on how the ultraviolet theory works. Okay, so again, if you think that the Standard Model is just the low energy limit of something more important, we should really look at this structure here and try to understand what it's telling us about the ultraviolet theory. As I said, and again, let me try to quantify the kind of tension or unnaturalness that we see. So here in the Higgs sector, we have the Higgs mass, this Yukawa coupling, and then in this series of higher dimensional operator, we have bounds. Okay. So what usually people call the hierarchy problem is the tension between this mass scale here, which is the Higgs mass, which is 125, and the scale of higher dimensional operator, which describe, if you want, generically heavy masses, that if I forget about flavor, if I look at, for instance, interaction of the gauge boson and so on, this bound is few TeV. Okay, so there is some tension, which is not terrible, but this is the hierarchy problem. The other two problems are related to flavor. And one is the standard model flavor problem, that is, we have this Yukawa coupling, which, as I said, they span 5 order of magnitude from the Yukawa coupling of the electron, which is 10 to minus 5, to the Yukawa coupling of the top, which is 1. There are 5 order of magnitude. Why this is so? It's very unnatural. And last, there is this new physics flavor problem, which actually, so we seem to see from the flavor observable here, for fermion interaction, bound on the scale of new physics, which are much higher than those from the Electroweak sector, even up to 10 to the 5 TeV. So this poses an even more tuning problem to the Higgs mass. So I mean, again, what keep separated this scale here from the Higgs mass? Because there is a coupling between the Higgs and the fermions, so it's difficult to keep this scale separated. So you see, this is the kind of unnaturalness of the standard model seen as an effective theory. As I said, this problem have been with us since a long time, and we try to solve it in different ways. But one approach which has been popular for a while was the idea of minimal flavor violation, which was very popular in the pre-LEC era. Which was the idea? The idea was, okay, maybe really this pattern, this strange pattern, it's something that happens at very high energy scale. Okay, it's an imprint of something happening at very high energy scale, and that then, so the flavor structure are generated at the hemisphere, so we cannot see a different type of mixing except those in the Yukawa coupling. And the new physics, so there is some new physics around the few TeV scale, is completely flavor blind, so feels the breaking of the flavor only via the Yukawa coupling. So again, this is a way to separate the two problems. So separate the stabilization of the Higgs from the generation of the flavor structure, which is a possibility, technically works from the point of view of quantum field theory, because these are indeed are adimensional couplings, so they can be generated by very heavy dynamics, and we would not be able to probe it. It's a possibility. Now this has become much less popular, okay, after the LHC expanded, because this idea would have been worked well if we would have found new physics at few TeV to stabilize the Higgs that we have not seen. Okay, and actually the bound on new physics becomes even stronger if you make this assumption, because then it means that new physics couple in a universal way to all the families. Okay, then people start to be, okay, pessimistic if you want, and then propose a completely different idea, that is, which I don't like, as you see it here, which is say, well, maybe the model is really tuned. Okay, then forget to try to predict this parameter. They're tuned, okay, and or they're just determined by kind of anthropic argument, which I think is basically giving up trying to solve the problems. Okay, you say, okay, it is what it is, and we keep it like this. So I don't want to pursue this idea further, but I should say it's something that now people are taking more seriously. Maybe really the discoupling are kind of anthropically selected. I think the third way, which I want to advocate in this seminar, is the idea that maybe it was wrong trying to separate the two problems. Maybe the new physics that is there really see the different families in a non-universal way. So the fact that here we have some small coupling, maybe this is a remnant of the fact that there is some UV, which however doesn't speak with the light families, it speaks only with the third families, which has a big coupling. So actually, if you think that this coupling, which actually are the only known gauge interaction in the standard model, are really the remnant of the interaction of some heavy degrees of freedom, I think it's very natural to think that these new degrees of freedom will see the fermions in a non-universal way. So they don't couple only with the standard model gauge quantum number. They will couple in a different way. So they see the third family in a different way than the other families. And this is, so again, why these coupling are small for the first families and light and bigger for the third families. And this is nice because actually, okay, it tells us that we can have some new physics at the few TeV, because actually if these new physics talk with the third family, it can be much lower, given the information we have from LHC. And actually, what we start to see in B physics maybe is really the first evidence of this new physics around the few TeV, which we need to stabilize the Higgs sector, and which explain why we can see it only in the third generation because it's a non-universal physics, some physics that really see the families in a different way. Okay, so this was a kind of general motivation. I hope I didn't lost too many, although it's really based on this effective theory argument. Let's now, okay, go a bit close to the data. So why are these exciting things which let us to think that there is some indeed evidence of new physics around the FTV in the flavor sector? These are these interesting evidence of breaking of universality in BDK. So lepton flavor universality anomalies in BDKs. So recent data show some, in my opinion, convincing evidence of lepton flavor universality violation in semitonic decays of the big quark. Actually, all the data, I will be brief here, but I want to summarize the key point. Data seem to show a different behavior of the different leptons in semi-leptonic BDKs. So here we have two types of evidence. In the case of B going to charm decay with the leptons, we seem to have a different behavior of the tau, so the third generation lepton, with respect to the light leptons. And in these B2S LL decays, we seem to have a different behavior of the muons with respect to the electrons. So we go back to the famous who ordered the muon, because the muon is something different, it's different from the electron, okay? Which seems this data, so it's very exciting. So what the experiment measures? So again, on this B2 chart observation, the experiment measures this ratio. So let's say a B meson decay to a given hadron, a D or a D star, and the tau on the same process with the same hadron and the different lepton. So in the standard model, this is mediated by the W. The W see the different lepton exactly in the same way. So if it is a tau or electron, a muon, no difference. On the other hand, when you try to normalize to the, so you make this ratio to cancel the hadronic uncertainty, so you get a good prediction. Here you see the combination. This cross here is the standard model prediction. This is the combination of all the experimental result, which different from the standard model by more than 3 sigma, okay, 3.1 sigma, which is not super strong evidence, but it's 3 sigma, so it's not small. And you can explain this if you assume that there is some new physics only in the tau, okay, because actually the electron and the muon seems to be well behaved. And you see that the data seems to show a consistent universal enhancement. So in the end, the star, which is left-handed, okay, because actually this correlation is what you expect from a left-handed interaction. So new physics seems to show something like in the standard model, but different in size for the tau. Okay, so this is the first sector, B2 chart. And the next thing is that we will have new data very soon on this, okay, so hopefully even at the next winter conference. Then there are the B2SLL anomalies, which actually are the oldest set of anomalies, and the one which is more rich. Actually, here we have a lot of different observable. So the angular distribution in B2K mu mu, the smallness of the branch ratio, and finally, lepton flavor universality ratios, okay, in B2K star LL and B2K LL. And finally, the absolute rate of BS mu, which, so all these process, all these observable are sensitive to the same BSLL amplitude. And I put them here in chronological order because it is how the things were measured. So actually BS mu is the last one in terms of precision. But this is not the same order as precision. Actually, the cleanest observable here are the lepton flavor universality ratio. Okay, so again, a ratio where you look at B2K mu mu versus B2K EE and so on. These observable, some of these indeed are more complicated because here this is not a 3-level process, it's a 1-loop process in the standard model, so which is more rare and is also more difficult to compute. But when you take the ratio, you cancel a lot of the uncertainties. So let's look at the ratio. So the ratio are this ratio B2 hadron mu mu over B2 hadron EE. The hadron can be K star. You see here is the standard prediction and here is the observation. Again, here the standard prediction and here the observation. The observation is systematically lower. 2.2 sigma in one case, 2.5 sigma in the other case. So again, nothing too striking, but one, you can combine it together. They go exactly in the right direction. And the interesting thing is that there are other anomalies in the angular distribution. And what one can do doing a precision fit of all the observable is that these lepton universality breaking effect are described by the same set of, if you want, interaction that describe also the anomalies which I mentioned at the beginning in the angular distribution and in the branch ratio. And everything seems to point to the fact that there is a new interaction only in the muon, okay, and not in the electron. And actually, the significance of the anomalies has not increased a lot in the last release of data, but again, we expect a new release very soon. But the picture has become very consistent when you put all the observables together. In particular, there is this new ingredient in the game, which is the suppression of BS mu, which is also, again, a 2.6 sigma. So when you put all these things together and you test the standard model hypothesis in a very conservative way, I want to stress this, in a very conservative way, without making assumption on the form factor, you find that the evidence here is 4.2 sigma, which is quite big. And this is without assumption on the form factor. If I do assumption on the form factor, very reasonable, I get higher significance. So I think it starts to be really interesting. Okay, so this was just a flash on the data. So I hope I give you a hint on the fact that this recent data shows some convincing evidence of a non-universal behavior of the lepton in this process, B2 char, B2S LL. So what is nice of these anomalies is that compared to other anomalies we've seen in the past, they're really challenging one assumption that is a kind of standard assumption in many analyses, that is the fact that the leptons behave in a universal way. We tend to give this for granted, okay, that has to be like this always, that we basically electron and muons are identical copies, okay, except for the mass. And somehow we never questioned this assumption, which on the other hand, these data now are interesting because they let us thought that maybe we have to question this assumption. And now we realize that this assumption, we give it for granted without many strong theoretical arguments. There is no real need to make this assumption that the electron and muons are the same thing except for their mass. Actually, this is a kind of accident that we have in the standard model. So, and then indeed, I think from this observation, we derived recently I think one can derive three messages for model builders, for those who construct physics beyond the theories beyond the standard model, which are very important. And I think will remain even if eventually these anomalies will go away, because I think this questioning this idea of universality, which was kind of given for granted, has been very, very beneficial in thinking of new ideas. And so the three messages I think which we can extract from this are listed here. So the importance of the possibility of flavor non-universal interaction, the role of flavor symmetries, and the role of leptoquark. And so let me try to go one by one. So the most important is this idea of flavor non-universal interaction, which I think it's really a bit different view on model building, okay, with respect to the standard things which was done till very recently. I think this is why I like to show it's a kind of turning point in the way you construct models for physics beyond the standard model. As I was saying at the beginning, I think most of the model building attempt, at least especially recently, was based on the following idea. Okay, concentrate on the Higgs sector, try to stabilize it, forget about flavor. Okay, basically giving for granted that the three generations are identical copies, but for mass terms which are not very relevant. Now, these anomalies are telling us this is a wrong assumption. If you take these anomalies seriously, that's not the case, because we really seem to see an interaction which distinguish the different generations. Okay, so it could be that this universality that we see in the standard model is only a low energy property. So let me elaborate a bit more on this to give you an example, what I mean by non-universal interaction. So, forget about just concentrate on electromagnetism, okay? When we look at electromagnetism, of course, we know that there is the photon, that of course the photon see in a completely identical way the electron left and the electron right. Actually, they are the same particle from the point of view of electromagnetic interaction. But we know that at high energies, the electron left and the electron right are two completely different fields, okay? And they are and the photon itself, it's just a diagonal generator between two different gauge groups, which see in a different way the electron left and the electron right. So when we go to high energy, in a sense, we resolve this. We realize that this degeneracy of electron left and electron right and their universality from the point of view of the interaction was a kind of an accident. Well, it was an accident. It was the long-range structure of the model, but it's not the U ultraviolet structure. So the same could happen here, that you see we can consider the set of standard model gauge boson as the kind of the long-range structure which sees accidentally the electron, the mu, and the tau as identical from the point of view of the gauge interaction, but maybe they are structurally different. So there are new type of interaction which see the different generation in a structurally different way. So the apparent flavor symmetry of the standard model could be an accidental property which holds at low energy only, because it's dictated only by the charges of the particle under the long-range forces. Doesn't tell anything about the ultraviolet structure. So coming back to this general argument, I think the message of this anomaly, in my opinion, is that we should not ignore the flavor problem. There can be new interaction already at the TV scale, distinguish the different families. And actually, this is good also to attack the hierarchy problem, because a different behavior of the third family with a special role for the third generation, it's important to understand the hierarchy problem of the Higgs, because the Higgs indeed is related to the coupling to the top. I mean, that is what destabilizes the Higgs, not the coupling to the light furnace. Okay, so this was the first point. Let's now go to the second point, which are flavor symmetries. Now, as I said, these anomalies are seen only in semi-leptonic process. Okay, and actually, what we seem to see is a non-standard, if you want, a new type of Fermi interaction between quark and lepton with a specific flavor structure, and that seems to involve at least left-handed field. Maybe there is something else, but for sure has to involve left-handed field. Now, what is the flavor structure here? Sorry. The flavor structure here, this I, J, alpha, beta, denote the different flavors. We need a large coupling in the case of this B2 Sharp anomaly, because here we have to compete with the standard model at the 3 level. Okay. Note that this process, B2 Sharp tau, is a process where we have several fermions of the third generation. So the B is the third generation, the tau, I call it L3, but this is the tau. So it's the third generation and neutrino third generation. And we have only one second generation field. Then we have a much smaller effect in the case of B2S muons, because here we have one third generation field and now several second generation field. Unfortunately, experiments are not able to see the tau here because it's very difficult experimentally. It would be extremely important, but we have very, very weak bound there. So you see, this is nice because it seems that the more we have third generation field, the more we have something big, the smaller is the effect. So the idea is that we have maybe an interaction which is, let's say, 1 in some unit for the third generation when I have all third generation. And then there are smaller mixing type effect when we go to lighter generation. And this is exactly the same pattern that we observe in the Yukawa coupling. You remember there was the big Yukawa coupling of the top and then so on. So this naturally points to a possible link between these anomalies and the origin of the Yukawa coupling, which is nice. So we connect to the old standard model problem. Now, to fit the data, it's trivial, okay, to fit these anomalies. What is non-trivial is to be consistent with all the other processes where we don't see deviation. So because there is a long list of constraints from other processes, like there are other semi-leptonic BDKs involving only light leptons, a lot of rare K decays, which are generically called flavor changes currents, okay, pion, kaon, tau decays, electroweak is observable. This is the difficult thing. I mean, not to put the coupling here to fit the anomalies is trivial, is to do it in a way that you don't disturb all these. It's complicated. And the only way to do it in a meaningful way is to assume some flavor symmetry, okay? A well-defined pattern that, again, maybe connect the anomalies with the Yukawa coupling and also explain you why you don't have a big effect in all these other processes. So which can be these flavor symmetries? Well, clearly we already understood what we have to do. We have to do something that distinguishes the third generation from the light generation. So the basic idea, the basic structure is a chiral flavor symmetry of the type U2. That is where these U2 act on the light generation, which are doublet of this U2, while the third generation is a singlet. So clearly in the limit of exact symmetry, you basically forbid the coupling of the new degrees of freedom with the light families. And this symmetry doesn't need to be a fundamental symmetry, okay? We don't want to gauge it. I mean, it could be an accidental symmetry. Maybe it's a kind of accidental symmetry derived by the structure of the gauge interaction. We will come back to that later on. So we have to introduce some breaking term of this flavor symmetry, otherwise we cannot generate the masses of the light family. So how does symmetry act? For instance, if you look at the up Yukawa coupling that we have seen before, in the limit of exact symmetry, I basically forbid all these entries here because of the U2 acting on the right-handed side and U2 acting on the left-handed side. So only the third generation Yukawa coupling is possible. But then I've introduced some breaking term, for instance, of this U2 symmetry here, and then I can introduce the mixing between the third generation and the second one, and finally also here the mass of the second generation. And then you remember these things we have seen it before. So we want to generate this structure because this is what we see in the Yukawa coupling. Okay. And so we know the size of these breaking terms because one is determined by the CKM matrix is VTS, which is 0.04. So this is this entry here. And finally, we have this, which is even below 10%. So this idea that there is a flavor symmetry and there are only small symmetry breaking terms of this type, again, was proposed long before these anomalies, okay? So it's nice because it's not an idea that was proposed to explain the anomaly. It was an idea that's proposed generic, consistent extension of the standard model that allows mu physics in the TV scale and are consistent with and explain the pattern of quark and lepton mass that we observe in the data. And so if we take this idea that again was proposed before, and now we build an effective theory based on the following two hypotheses, that we have this flavor symmetry and the breaking terms are exactly those that we see in the Yukawa coupling, and we put generic left-handed simultonic operator consistent with this flavor symmetry and the symmetry breaking terms, we can fit perfectly the data being consistent with all the bounds. And so you see here the result of a fit, which was already, now it's already 3 years old. We find that the scaling of physics is indeed in the TV scale. It's not too heavy, but we pass all the bounds, okay? It's nice. And it is the flavor symmetry that protect us to disturbing things like Big-Bar mixing and so on. And actually, this again was proposed already 3 years ago, and now more recent data have made this picture more consistent because actually, okay, now here I don't want to enter to the detail. This is just for the expert. There are some recent changes in the data, for instance, the emergence of a contribution from the B2S tau, which seems to be consistent to what we was predicted. Again, there was this suppression of BSP mu I told you already before. So everything seems to be coherent. Again, the significance is as I said, is 4 sigma in one sector and 3 sigma in the other. So actually combined, it's quite significant, and there is no problem with the data. And now, okay, so this is from the point of view of the effective theories. And now, okay, let's finally do the last step, that is try to build a dynamical model that explain these 4 fermion interaction. And here is where leptoquark come into play. So the question is, which mediator can generate these 4 fermion interaction that we will need to explain the data? Okay, it's interaction between quark and lepton. Of course, this can be done. There are not many options because we need a low scale, okay? Because we want to explain both anomalies, and so we cannot do it at the loop level. We have to do it at 3 level, so that we can have either Z prime type mediator or leptoquarks. And leptoquarks have a strong advantage here because they explain naturally why the effect is seen only on simultanic operator, because see, the leptoquark, when you generate a 4 fermion interaction, is only simultanic operator. We don't have for quark or for lepton. Well, in this case here, if I take a Z prime, for instance, here you see a Z prime, I can have, if I have coupling to BS mu mu, I should also have a coupling to BS BS, which is bis-base mixing, and this is highly constrained, while for the leptoquark, bis-base mixing enter the 1 loop level, and it's much smaller. And this is good because here we don't see anything, while here we see something. So clearly the leptoquark is favored just from empirical fact, from comparison with data. And also for the direct searches, I mean, a Z prime, it's more constrained by direct searches at LHC, while the leptoquark much less. Now, I would say leptoquark is a strange beast. I have to admit that I was not a fan at all of the leptoquark till 3-4 years ago. And indeed, I always like to say that leptoquarks suffer a kind of underserved bad reputation for two reasons. One, because they can mediate proton decay, which is bad, because we know proton do not decay, at least for a long time. But this is not a general feature of the leptoquark. There are indeed nice leptoquark which do not generate. This is a property of the gauge group where you put your leptoquark. For instance, you put in the Patti-Salam, the proton is perfectly stable, exactly like in the standard model. So there are different types of leptoquarks, and this is important to realize. And the other problem of leptoquark, for instance, was in flavor, like process like K-long to μe. But here again, it's not the leptoquark the problem, but it's the flavor structure. So if you do it a non-universal interaction, you can solve this problem. So this is why indeed there's been a renaissance of models with leptoquarks in the last few years, where in very different contexts. Now I don't have, of course, time to discover them all. I just want to give you a glimpse that indeed there's been a lot of literature of model of leptoquark, because indeed we realized, rediscovered the fact that leptoquark are very nice and indeed could hide very well in direct searches and could explain well these anomalies. Okay, so the last things I want to show you now is really more speculative, is a class of models with leptoquark, which I find very interesting, with something which I work with my young collaborator you see here in this picture, which is a specific class of leptoquark models, which I find particularly interesting. So, and everything is based on two observations. So the first one is the fact that this Patti-Salam model, which I already mentioned, which maybe some of you remember, it was a model proposed in the 70s to unify quark and lepton, predict as massive vector a leptoquark, which is exactly the right quantum number to explain the anomalies. I mean, because as I told you, there are different types of leptoquark, but the one that perfectly do the two anomalies is only this U1 2/3 leptoquark, which is a natural generator of the Patti-Salam group. So, which is the idea of Patti-Salam? The idea is that we enlarge the gauge symmetry from SU3 to SU4. SU3 is the gauge symmetry of strong interaction. And the idea is that lepton number is the fourth color. This is the idea of Patti-Salam. So instead of having triplet of colors, you have now fourplet, okay, of colors and lepton number. And of course, you have to break this SU4 to SU3 color times U1 B minus L. And when you do it, you generate 6 massive leptoquark, which are exactly the 6 degrees of freedom that you need to explain the anomaly. So it's beautiful. However, the problem of the original Patti-Salam idea is that here there is no flavor. Okay, so this leptoquark is universal. So we'll couple to all the families in the same way with a unitary mixing. So you can play with mixing, but there is a unitary matrix. So you cannot kill overall the strength of coupling to the first generation. And then, for instance, process like K-long to μe, where you have where you have second generation of quark and lepton, first generation of quark and lepton. We don't see this process, K-long μe, and this put a very strong bound on a mediator that couple in a universal way to these families here. So we have to, I mean, it's nice, this idea of SU4, but we have to do something slightly different. Okay? We have to either enlarge the group or enlarge the matter content. So the second observation here is come to the fact that we need indeed to have this non-universality. So how we can do it? Well, the idea is that we have to, the simplest way to do it, and kind of also more elegant, is to enlarge this SU4 to something that can be SU4 times SU3, and this actually was something that was proposed again before the anomalies by these people. Actually, now, and Diluzio, Grelli, and Nardecchi proposed it after, realized that was perfect for the anomalies. And because this way we have the freedom of having a SU4 where, for instance, we charge only the third generation. For instance, here you charge the third generation only under SU4 and the other two generations under SU3. And then, of course, here there will be a diagonal generator, which is SU3 color. So, for instance, a construction of this type. So these are called 4-3-1 models. because actually it's SU4, SU3, SU2, and eventually here I can put U1 instead of SU2, right? But here again, the important part here is this sector containing the strong interaction and the leptoquark. Here there is a diagonal subgroup, which is SU3 color, but then you see you have this SU4, which you can couple it only to the third generation. Of course, you have many more broken generators in this case, so you will have also massive gluons, which couple in a non-universal way to third and first generation. So this is, one has to check if this works, but I can tell you that that works. But so it's a more complicated model, but it's nice because it achieved this idea of non-universality from the beginning. So here, this U2 flavor symmetry comes naturally, accidentally, simply because you split the first two families from the third one. So from the gauge structure, you see that the gauge structure are compatible with a U2 symmetry and not with the, because we charge in a different way the different fields. Now, what has to do, well, people have, in various groups, went above this construction limit to try to find UV completion of this more ambitious UV completion, which actually connect these models to a possible really explanation of the structure of the Yukawa coupling. And here, so there is a long list of models, which are all kind of generalization of this initial idea. And I will discuss in more detail one option, which is this Patisalam cube, okay, which is nice. Actually, you see, we basically do 3 copies of Patisalam, each one for each generation. And we are now working on discussing the possibility that this maybe is just a 5-dimensional, is a 4-dimensional view of a 5-dimensional construction. I will show you that in a moment. So, which is this idea of Patisalam cube. The idea is that we have different Patisalam group for the different generation. Okay, so it's shown here with this Moose diagram. So each fermion has its own gauge group. So the fermion 1 has the Patisalam 1, the fermion 2 has the Patisalam 2, and the fermion 3 is charged on the Patisalam 3. Then there are some fields that break the symmetry, which are scalars, and there are 2 types of breaking. What you can call vertical breaking. For instance, here I break the Patisalam 1 to standard model 1 with this sigma 1 field. It's a field that break Patisalam. Well, here on the other hand, I put the Higgs that break SU2 cross U1 to QED. Okay, and you see the Higgs, I put it here close to the third generation, while sigma 1, I put it here close to the third generation. So the idea here is that actually the more you move, the more you have weaker interaction. So the more these fields are distant in this diagram, the more the interaction is weaker. And then finally, we have these link fields that are breaking, let's say, Patisalam 1 times Patisalam 2 to the diagonal Patisalam. So combining these high scale breaking with also vertical breaking with horizontal breaking, you achieve finally a breaking down to the standard model. You see, with a third generation that feel more the breaking of the Electroweak symmetry, and the third generation which feel more the breaking of the Patisalam symmetry. So the third generation see less breaking of Patisalam, so indeed see the leptoquark, because the group is still see the remnant of SU4, while the first family doesn't see SU4 at all, and because there is a big breaking, and also doesn't see the Higgs, so we have light masses here. So you see, this is the nice idea of the construction. We explain also why the Yukawa coupling are light. So let me give you another picture to understand this without entering into the detail. You see here, again, this can be understood as a 4-dimensional description of a 5-dimensional picture, where we have indeed the Higgs field, which has a profile in the 5th dimension, localized more on the third brane, while the field that break the Patisalam are more localized to the 4 families. And the fact that we have different copy of the Patisalam is simply because we have a Patisalam gauge symmetry on the bulk, and we have different branes where we localize the fermions. Okay, again, this I think it's a nice idea, a nice construction, which if you want can be seen as a justification of the particle content on the 4D picture which I showed you before. Or actually, to do calculation, one really need 4D to do a precision thing. So let's go back to 4D. And as I said, we have different classes of models. So maybe it's a very complicated tree of theories, but at the end, all the theories have one thing in common, that at the end, around the TV scale, this is the gauge symmetry. It's the 4-3-2-1. So SU4, SU3, SU2, U1, with SU4, which is not universal, so it's only for the third generation. And finally, this you have to break it to standard model. When you do this breaking, you generate a lepton quark, a heavy zip, a heavy gluon, all around few TV. Actually, here I put 1 to 5, but actually it has to be 4 to 5 because now this is excluded to light. And one can put all the field to compute things. And the nice thing that here one is precise, so one can really do precision calculation. The parameter of the theory are fixed, most of them, by the Yukawa couplings. So you don't have many free parameters. It looks like a complicated construction, but at the end there are a few parameters. You can compute processes which in the pure effective theory are not precisely calculable, like delta F equal 2. You can make precise precision for the high PT data for the production LC, and everything seems to be consistent. So this is the message. I think is a very nice, very interesting construction, which should be seen. Okay, it should be around the corner, but it's for the moment consistent. So what we have to see, okay, of course, I mean, so this is a beautiful construction, as Feynman once said. I mean, can be, doesn't matter how beautiful the theory is, if you do not agree with the data, the theory is wrong. And so for the moment, okay, just fit the anomalies where we have to see, because we have prediction for a lot of things that should be seen pretty soon. So let's start with the high PT observable. So if ideally, if all this is correct, one should see this TV scale mediator soon. So you see this diagram here, where you see the mass of the lepton quark versus the coupling. The blue area is the one favored by the anomaly at 1 sigma and 2 sigma. These are exclusion bound. So from direct searches of pair production, this is where we are now. This is where we will go soon. This other bound is from PP to tau. So this is a T-channel exchange of the lepton quark. So you see, for the moment, the most favored region is not yet excluded, but at the end of the high luminosity phase, a good fraction of the region will be excluded. I will not discuss this, which is a different model, but you see here, anyway, it's not obvious that we will close completely the area, and it's not easy. You need the full high luminosity phase of LHC, which means still 20 years, okay? In the short term, on the other hand, still flavor observable, so low energy observable, are very interesting, because there are a lot of things that we should expect, okay? Because we cannot hide these new physics. It's somehow around the corner at the TV scale. So there is a super rich program for LCB, but also for BEL2 and other facilities. And this program is essential to determine the flavor structure of the new sector. So, and actually, and it's nice because here the prediction are even more precise than for high PT data. So let me just illustrate two things as a flash. For instance, this is something that we did very recently, computation of B2K neutrino and neutrino. So normalized to the standard model, you see one expect a 30-40% enhancement. This is perfectly within the reach of BEL2. And you see here, even more interesting, lepton flavor violation in B or tau decays. You see here B2K tau mu, or B sub S going tau mu. This is the bound from LCB, which actually is starting to cut the interesting part of the region, but you see the interesting dominant part of the model is not yet excluded, but will be probed soon, because actually we are here. So again, one expect here to see because of this non-universal structure, one has to see flavor violating the case of B meson, which will be extracting signal of all this. Okay, so I'm basically to the end. I hope I give you a feeling that flavor physics remain a very interesting mystery, and we don't have yet a fully clear answer for this puzzle of this standard model new physics puzzle, but it's clear this is an opportunity, and I think we should not really ignore the flavor problem. So this is really the message is that trying to postpone the flavor problem, so really assume that this is generated at high scale, miss a lot of interesting potential extension of the standard model, which actually are interesting. And these anomalies, albeit not statistically compelling yet, because indeed we are still discussing 4 sigma, provide a clear indication of that how flavor could be interesting. And if you take them seriously, if this will be confirmed, this will be really a clear indication of some non-trivial dynamics close to the TV scale with a non-trivial flavor structure. And I assure you that actually, from what we know, these anomalies are not in contradiction with all the other existing low and high energy data. And they point out to well-motivated new physics model, which could really address the flavor problem with this idea of non-universal flavor interaction. So I think there is a lot of fun because data will come, and so will tell us if any of what I just told you is true or not. Okay, so thank you for your attention.
Thank you very much, Gino, for this very interesting and clear talk. Now we collect questions, so anybody that has a question, please feel free. Harsh, you have a question?
Actually, I was just applauding, but I do have a question as well. So that was really beautiful, and I think one of the most exciting things is how much of this is accessible to LHC already and in the near future. But I was wondering if there are other, do these models that you built, do they have implications that could be tested in precision experiments or?
You mean beside LHC-P?
Yeah, like for example, atomic experiments. Well, you very low scale where you have new physics.
EDM,
well,
so.
EDM is a complicated. Let me say other things that, well, one key point is that here, by construction, these new physics tend to couple very little to the light families. Okay, and for the moment, we really don't have information on how much it's coupled, let's say, to electrons. So for the moment, this coupling can be 0, okay, or super small. But we know at some point you should couple because we see the non-vanishing mass of the electron. But actually, given the smallness of the electron you have a coupling, the idea is that indeed these effects are very small for the light generation. So I think it's much easier trying to see it for instance, precision tests with tau physics rather than in experiment involving electron only. Okay, this is, I don't have a precise, but for instance, one experiment which I think is very interesting, the one more interesting one on with electron would be mu2 That I think it's interesting because okay, at least there is or mu to E conversion in nuclei. For instance, there is an experiment at Fermilab. That I think is interesting because there you really test this mixing between the electron and the heavier families. So that could be within the reach of this experiment for reasonable values of the mixing angle. For EDM, also the CP phase is entered to the game, so it's even more uncertain. This is why it's even more difficult to answer. But
sorry, Harsh, I wanted to applaud at the end, but if you did before, we can do twice.
I will not hear the applause, so don't worry.
Alexi.
Yeah, thanks for the nice talk. So I have two maybe naive questions. So you mentioned that the U2 global group helps you predict the structure in the quark sector. So I'm wondering if there is something analogous in the neutrino sector.
That's a very good question. Actually, I had no time. I probably already put too many things for the neutrino, but we spent a lot of time. I discussed this with Pavel before the seminar, and so for the neutrino, the structure would be interesting in a sense that because of Pati-Salam, we expect attending neutrinos with the same mass somehow, I mean, around the TV scale, actually, at least for the third generation. So we expect some attending neutrinos at the TV scale, and then for the other families, a bit heavier, but still not at the GAT scale, the classical GAT scale. So the way to do it actually is along a way that was suggested by Pavel and Mark Wise some time ago of doing a inverse seesaw, which in Pati-Salam work very well. And this here will be a series of 3 inverse seesaw for the 3 different generations. So for instance, the prediction is that we should expect some deviation from unitarity in the PMS matrix because of this fact. So there is some observable consequence. We estimated this to be Okay, for the moment it's consistent with present data, but say if one could improve by 1 order of magnitude there, one should see something. And also one should see a heavy right-handed neutrino at the TB scale. I would say here the connection to the anomalies is not straightforward, but I think this idea fits well. Okay.
My second question was about the U1 gauge boson that you showed some range where you can explain the anomalies. So I'm wondering if there is an upper bound on the mass of the U1 such that you explain the anomalies.
Well, from the EFT, you just measure a ratio between coupling divided by mass. Okay, so maybe I can, let's see if I do you see still my slide or not?
Yes.
Yes.
You see this actually for me I see. Okay, you see when I go for instance to a mass of 5, I need a coupling between 3 and 4, which is still semi-perturbative. If I go to 6, 7 TV, it's completely non-perturbative. So then I really lose the predictivity. Let's say I think 5 is more or less an upper bound where you still have a perturbative description.
Okay, thanks.
Any question? Let me see, maybe I'm missing somebody. Okay, maybe I'm missing. Just a small comment, Gino. Thank you again for the talk. Clearly, if these anomalies are real, somehow, as you mentioned many times, the third generation is special, right?
Yes.
Then I was wondering, there are some ideas. Actually, I believe the first person did that was Barbieri. And if you treat the third generation as something special, you could imagine a theory where you generate the masses of the third generation at 3 level, and the other families will get mass at low levels, at a quantum level, right? I always like this idea due to the, because it's normal the top cover is so large that it's not a surprise that at 3 level you will get mass for the top. But the anomalies clearly they need more than that. They need a mediator that can give you the right channels to fit everything. Is there any theory where you can have this natural connection between? Because of course I can have 3 different scales, but then you are assuming that the scales are different because the masses have to be different. But if I am able to build a theory where the first and second family are getting mass at the quantum level, not the classical level, clearly that could be even an extra plus because I don't need to introduce so many scales in the theory. Is there anything like that in the?
I think this is interesting, and I don't know any attempt in this direction, but indeed it could be
combining of course all these ideas that you mentioned to do the job for the anomaly.
Indeed, I discuss. I continue to discuss a lot with Riccardo Barbieri because this idea of the U2 flavor symmetry was indeed. I think I remember we discussed when it was now it's already 10 years ago because indeed he was convinced that the third generation has to be special. And then I was convinced that we have to have a kind of minimal favor violation. And so the merging of these two ideas, we generated this U2, we came out with this U2 flavor symmetry, which is a way to keep the third generation separate from the others. So again, it's a static symmetry, okay, without dynamics. But, we are convinced that one has to find a dynamics that mimic this, okay? That is pretty clear from the data. If you want to, with these anomalies, especially with this anomaly, the scale of physics is relatively low, you need to find an underlying theory that somehow mimic this U2, so the small breaking of the first two family. And it's, what you said, I think is interesting. It's, but I don't know of any explicit attempt in that direction recently.
Any other question? I am missing, maybe it's hard to follow sometimes. Okay, Harsh, you want to say something?
Well, if there aren't any other questions, of course, if somebody else wants to go, I'm happy to yield. But yes. Otherwise, I just had a sort of more, I guess, philosophical question, which is that I think you listed all the problems of the world, and then you said you're going to look at just these 2 and try and focus on them as the most promising. But also you several times alluded to the fact that you came to this somewhat reluctantly to, the left to quark and so on. So I was wondering if you have thoughts about those other problems and how this, let's say this model is vindicated, how does that, advance the...
No, well, indeed, I try to tell you that really, I honestly, as I came to the things in a sense that, for instance, on the left of work, I was reluctant to accept it because, but in a sense, for me, it's already a step forward to put the two problems together, which again is not what many people do. And again, this is something I discuss a lot also with my collaborators. The point that these two problems, I think, is at least indicate, well, also with anomalies, it's nice because we have indication of scales. So this is all the Higgs, okay, clearly as an indication of a scale to stabilize it. This anomaly seems to go close to that scale. So this is why it's natural to put these two together. Problem like dark matter, I really don't have an indication of a scale. So I think it's a fundamental problem, but I think I would not for the moment, let's say, throw away the model because it doesn't address this, because there are so many other ways to do it, which I wouldn't do it completely. Already neutrino, it's a kind of something intermediate, because indeed neutrino is also a problem. For instance, okay, in the last paper we tried to put the neutrino into the game, and we realized that indeed with this CISO, inverse CISO, we can put it, and but it's already a lot of things which are not directly related to the anomalies that we have to put. I think it fits well, but there could be also other solution, okay, to the thing. This is why, again, I don't want to commit to things like dark matter, not because I don't think it's interesting, but simply because we miss really an indication of a scale there. From a point of view of effective theory aficionado like me, that I really want to see something that I can formulate as a well-defined problem as a scale in my effective theory. And these are the two problems. On the other hand, I think I can formulate the problem in a quantitative EFT way, and therefore this is why I think it should be put together.
Okay.
Alexi, do you are still asking a question? I see your hand. You raised your hand.
No, sorry, I forgot to lower the hand in the Zoom.
Any question from the students? Because good to give priority to the students, but sometimes we go. Yes, hard say. Anybody that has to go, please feel free. We know that.
Yeah, maybe we should switch to the sort of private conversation at this point, and take the opportunity to, make the really underwhelming applause that we can do on Zoom.
Yeah, well, I only can do this.
Yeah. All right. Well, thank you.
We can all do this.
Thank you so much.
Thank you.